Welcome back from the break, Matrix. I hope you guys are still enjoying the lesson. Thank you so much, Nicola, and over to you.
Thanks so much, Luni. All right, so let's get going with the last segment. We're going to be doing a 3D trig question, and then we'll do a little bit of Euclidean geometry. Okay, so this is the 3D trig question, and we're told that points L, M, and N are in the same horizontal plane. Don't forget, this is horizontal, that's vertical. And KL is a vertical tower. All right, so let's have a look at that diagram. So you really need to kind of like zone in on it and imagine that this is sticking out. There's your L, N, M in your horizontal plane, and this is the vertical tower over there. Okay, we're told that NLM, first, the angle of elevation of K from M is Q degrees. Angle NLM is P degrees. NL is equal to NM is equal to D. And KL is equal to H. And I think that's all on the diagram. Okay, so we can see our various angles. That's P over there. That's D. Okay, those are equal, so that's also D. And that's angle Q over there. Yeah, I think that's it. Okay, so the first thing we're asked to do is to determine the size of angle LNM in terms of P. Right, so angle LNM is this angle over here. And this often comes up that we have an isosceles triangle, especially when we need to use the sine rule in trig. Okay, so we're going to focus our attention on this triangle over here, which is on the horizontal plane, and it's triangle LMN. Okay, so we know one of the angles in that triangle. In fact, to help us understand, I'm going to draw the triangle over here. I'm going to remove it from the diagram and draw it outside. So we have LNM. We know that this is angle P, and we know that those two sides are equal. So effectively, we're working in an isosceles triangle. Because it's isosceles, we know that this angle is also equal to P degrees. And the angle that we're trying to find the size of is that angle over there. So we know that the three angles together, so angle LNM, which is the angle we're trying to find, plus this P, plus another P, so plus 2P, is equal to 180 degrees. And that is because the sum of the angles in a triangle is always 180 degrees. So therefore, LNM is equal to 180 degrees minus 2P. Okay, so not too bad. Okay, so the next question asks us to prove that LM is equal to D times sine of 2P over sine of P. Okay, so what we've just found is that this angle over here is equal to 180 degrees minus 2P. And we're trying to get the length of this side over here, LM, and we're trying to get it in terms of D and P. So we're going to use the sine rule, and the reason we're going to use the sine rule is because we have the angle opposite the side we're looking for, and we also have the angle opposite D, which is equal to P. Okay, so we're going to use the sine rule in that triangle. So I'm going to say that LM over sine of the angle opposite it, which is 180 minus 2P, that is equal to side D over the sine of angle P. All right, so sine of 180 minus any angle is always just the same as sine of that angle. So I can reduce that to just sine of 2P. So therefore, LM over sine of 2P is equal to D over sine P. And the last thing I'm going to do is multiply both sides by sine of 2P in order to get rid of that denominator on the left-hand side. So therefore, LM is equal to D times sine of 2P all over sine of P. Okay. And now the last part of the question asks us to show that H is equal to 2D times cos of P times tan of Q. Okay, so when you see the word hence, it always means that you're going to use the information in the previous question in this question, or in the previous part in this part. Okay, so looking at what H is, H was the length of that tower. So KL is equal to H. So KL is a length of this triangle over here, and this is actually a right angled triangle. And in this right angled triangle, we know that we have angle Q. Again, I'm just going to draw the triangle over here. So right angled triangle, we have H over there, we have angle Q over there, and then we have LM down here. And if you remember, we've just found or just written LM as being D times sine of 2P all over P. And the really great thing about this question is we're in a right angled triangle, so we can just use our trig ratios as they are. We don't need to use area rule or cos rule, anything like that. We can just go ahead and use one of the ratios. So if we look relative to side Q, we're working with the side opposite and we're working with the side adjacent to it. So therefore we're using our tan ratio. We're going to find what tan of Q is. And we can therefore say that tan of Q is equal to the side opposite, which is H, over this adjacent side, which from the last question we know is equal to D times sine of 2P all over sine of P. Okay, so let's just finish it off on the next slide. So we know that therefore H is equal to tan of angle Q times, and the reason we're multiplying is if we go back, we need to multiply both sides of the equation by this denominator. And that way we're going to isolate the H and we're going to bring this over to the other side. Okay, so we have tan of Q times D times sine of 2P all over sine of P. And the last thing we need to do here to make this expression look like we want it to look with a cos is we need to rewrite the sine of 2P as 2 sine of P times cos of P. Okay, so therefore H is equal to tan of Q times D times 2 sine P cos P all over sine P. And those sine P's then cancel, so finally we can say therefore H is equal to 2D, 2 times D times tan of Q, there it is, times cos of P. Okay, so the last question, which is our Euclidean geometry, we're given some information about our diagram. Okay, there's our diagram. Let's read what we need to know about it. So we're told that O is the center of the circle. We're also told that PQRS is a cyclic quadrilateral. And then we have the tangent through P intersects line RS produced at A. Okay, so we have center, we have our cyclic quadrilateral, we have our tangents, and the last bit of information is that OB is perpendicular to PR and that PA is perpendicular to AS. All right, so that's all in our diagram over there. And the first question is that we want to prove that triangle APS, which is this, APS is this triangle over here. We want to prove that it is similar to triangle BRS. So BRS is this triangle over here. So we don't have any information about the sides of these triangles, so we're going to have to prove the similarity using the fact that they're equiangular. So that's what we're trying to show, that they're equiangular. And we know that each triangle has a right angle, so that's really good news, makes our lives a bit easier. We also know that this angle over here, P4, according to the tan-chord theorem, is equal to that angle R1 over there. And then because the sum of the angles in both triangles is 180 degrees, this angle over here, oh, let me use my blue, this angle over here must be equal to this angle over here. So I'm going to write that all nice and neatly now. Always in geometry, you're aiming for neatness and logic. Okay, all right, so I've got in triangle PAS and triangle RBS, and don't forget to link the angles. So the angles must match when you write the triangles out like that. Okay, so I've got angle A is equal to angle B2 is equal to 90 degrees. and that's given. I know that angle P4 in my blue triangle is equal to angle R1 in my purple triangle, and that's because of the tan chord theorem tells me that. So therefore, angle S1 in my blue triangle must be equal to angle S3 in my purple triangle, and the reason for that is the sum of the angles in the triangle, in both triangles, is 180 degrees. Therefore, triangle PAS is similar to triangle RBS, and the reason is that they're equiangular. So you can say AAA. Some people like to write the angles out like that, and either is absolutely fine. Okay, and then the last question that we're going to do today is that we need to prove that AP times RS is equal to BR times PS. So if we look at what we've just proved, we've proved that triangle APS is similar to triangle, sorry, I'm just going to go back here, BRS. Okay, and when you're using your similarity to find these to find the product of the sides, you can always just use your little rainbows to link the corresponding sides together. So AP in the one triangle links with BR in the other triangle, and PS in the one triangle links with RS in the other triangle. So therefore you know that AP in this triangle over BR in this triangle, so remember AP links with BR, must be equal to PS in the first triangle over RS in the second triangle. Again, those two link. So use your rainbows to link the sides together like that. It's really useful. Okay, and then all we need to do is multiply both sides by RS first. Okay, and then we can also multiply both sides by BR. So effectively, we're just eliminating both of those denominators there. So the BR cancels with that on the left. And then finally, we have RS times AP is equal to PS times BR, which is exactly what we were asked to prove. All right, so that's the end of the revision for paper 2. I really hope it's been useful and that you've been able to learn a few things about geometry and trig. I wish you all the best for your exams. Don't stay up too late, rather get an early night's sleep and get some rest. Maybe do a little bit more revision, and good luck for your final exam. Okay, over to you, Luni.
Thank you, Nicola. Guys, it's been a great show. I hope you enjoyed it and you took as much information as you can to help you prepare for your exams. Everything of the best, and if you have any questions and comments, remember to send those through and we'll assist you as much as we can. Congratulations to all of our competition winners who will be announced on our Facebook page after the show. For more revision, please visit our website on www.wazamatrix.co.za, and if you missed any of the shows, they are available on our YouTube channel. Well then, from me, Luni, Nicoline, and Nicola, thank you and goodbye.